So I just started the recording here. If there are no questions, again, you can chat privately. You can email. You can send comments in Google Classroom. Do make sure that you reach out if you have anything you notice, and do look for things to notice. Again, I'm not doing any April Fools here. If there is a mistake, it's a mistake. There's no effort to have anything wrong there on purpose. So, all right. Well, let's look at something much more interesting, which is acids and bases. Acids and bases. Acids and bases are a lot of what we use in chemistry because it moves around the simplest element, which is hydrogen. It's the most common element, and it is all over the place, even on Earth, because it was able to get bound to oxygen, which is the most common element in the crust. And so when hydrogen, the most common element in the universe, gets bound to oxygen, the most common element in the crust, what do we get?
Excuse me, Mr. Bowden.
Hi, Isaac.
Yeah, I was wondering, could you please now mark me late because I was having internet issues this morning.
All right, thank you. Yeah, I'll make a note of that.
Okay.
Thanks for making it here. So again, we put together the two most common elements, one in the whole universe overall, including in our solar system, which is hydrogen, and we put it together with the most common element in the crust, which loves to bind to metals, which is oxygen. And what do we get?
Water?
Water, exactly. And water loves to stick to itself. It's got that hydrogen bonding with it. Remember those van der Waals forces, the intermolecular forces, the London forces, all of those things keep things together. Otherwise, you know, the whole universe would just be evenly spread out with all the atoms, and molecules maybe. But they do clump together. And as a result of that, water, even though it's really, really light, it's only 18 grams per, a mole, which we'll get to that, what that is soon. Anyway, even though it's really, really light and it should float away, it doesn't because it is able to stick to each other. Each molecule is able to stick to other water molecules very well. And so we've had water here on the world, since the beginning. In fact, just yesterday or the day before, there was another article out about how in the Archean eon, which was the second of the 4 eons we've had here on Earth. We're in the 4th one right now. But anyway, in the second, the whole world was covered with water, evidently. And only gradually has continental crust been able to rise up out of the water. So I thought that was interesting. So in any case, water loves to stick to each other, stick to itself, and it's got hydrogen in there, and water is a great source of hydrogen if other things want hydrogen more than water does. And if they don't want hydrogen as much as they've got it, water will gladly take it off their hands. And so this is a big deal. And so as we are looking at acids and bases, it's not just some random thing in the corner of chemistry. This is a very central thing to chemistry because almost all chemicals will involve some sort of movement of hydrogen at some point. All right, let me just shrink this down just a hair. Okay, there we go. All right, what do we have there? What's that a picture of? Soda, yeah, soda. Some people will call it pop, but some people will call it other things. But yes, soda. And let me see here. Just trying to see here. Okay. Looks like we're as loud as we can get. Okay. You're just coming in a little quiet there, but that's okay. Yes. And so we have acids in soda. it says that there's a certain acid, but actually there are several acids in soda. And you can see that quite easily if you just look at a can of soda. And I'll grab one myself. I think I've showed this to you before, but so, you've got your nutrition facts here. And I'll read the acids that we've got there. We've got phosphoric acid. And phosphoric acid is going to have which element at its core?
Would it be phosphorus?
Phosphorus, exactly right. And then we've got, let's see here, sodium benzoate, which is kind of the alternate form of benzoic acid. We've got carbonated water, and hidden in that is actually the fact that it's got carbonic acid in there, carbonic acid. So we've got, which would focus on the carbon there. So we've got carbonate, we've got phosphate, we've got benzoate, and if you just add a hydrogen to those, or the right number of hydrogens, then you've got their acids. And we have all these acids in sodas. We don't really have a bunch of bases. Our stomach already has acids. Why would we want to add more acids to our acid? Why don't we want to have a basic drink? Sometimes people do have a basic drink. Does anybody know any basic drinks out there? Alkaline. I'm going to take that silence as a no. And one reason we like acids is because our tongues interpret those hydrogens that are coming from the acids as being sour. It sends a signal to our brain. Our brain interprets that as sour. And sour can be bad. You put a whole lemon in your mouth, of course it's bad. It's a bit too much, but generally we like it. Something about it has made something pleasant happen in our brains. The opposite, which is something basic, where it takes away hydrogens or it provides hydroxides, that makes things bitter. And so when we our tongue, the taste buds on our tongue, the chemical reactions there when you add a hydroxide or OH minus, or you take away a hydrogen, when you do that, then all of a sudden those send signals to our brain that most of our brains anyway don't interpret positively. But interestingly enough, a lot of that is actually culture. Some places they actually like to have bitter vegetables. Something about it is actually pleasant to them. So pleasure and good are not necessarily the same thing. So that's a little philosophy for you there. Pleasure and goodness are not the same thing. But anyway, we do like, generally, here in America, we do like soda pop, Coke, whatever you want to call it, that is sour. There is, once in a while, people will drink a basic drink if they have acid, too much acid in their stomach, and it's kind of coming up their esophagus, giving them heartburn. Has nothing to do with the heart, but it's near the heart. It's in their esophagus going up to their mouth. Anyway, they will take a basic drink at that point. And so maybe a little bit of Maalox or Alka-Seltzer. And but you don't usually drink those things for pleasure. Yeah, all right, that's enough about that. All right, so how do you know the name and the formula of an acid? Okay, so just like the previous two sections where you're giving names to things, or you're taking the name and getting the formula, there is a method, and it is a method you can learn. All right, so what are acids? Well, they are ionic compounds, usually. Anyway, and they are, just a moment here. Okay. And the idea there is that they will make hydrogen ions when dissolved in water, and I've already said that. And later on, in the school year, we may get to other definitions of acids, but just what I've said so far and what it says on the slide here, they provide a hydrogen ion. Okay, thanks for letting me know. Okay, so very useful. They clean things. Sulfuric acid etches circuit boards. All right, and what that means is that they make the lines clean and straight, make it so that when you shoot electricity through all of these circuits that are in computers, they go where they're supposed to go, and they don't foul up. You may not be amazed by circuitry, but there are people alive today still who were alive before the very first circuit was ever made. Millions of people, in fact. And this is still a new and evolving thing. All right. Now, back to naming the acids, the actual process of doing it. You have an anion, like I mentioned, phosphate, benzoate, carbonate. Those are all 8s. That tells you that they're ions that are chock full of oxygen, element 8. And anyway, it's an anion combined, so let me just bold that, combined with as many hydrogen ions as needed to make the molecule electrically neutral. So hydrogen ions, that's H+. Let me just put that in there too. H+. Oops. All right. And again, electrically neutral, so there's no charge over it. So phosphate, which you know is PO4, has a charge of 3-. So in order to get it to be neutral, to have a charge of 0, it would have to have how many hydrogens? Okay, I'll ask that again. If I have phosphate, which has the formula PO4 and a charge of 3-, how many hydrogens, or H pluses, would I need to make that -3 become 0?
3.
3, exactly. Thank you, Layla. Right, 3. So 3 positives cancel out 3 negatives, and then you've got good old phosphoric acids. Yes, thank you for those of you who put the answer in the chat as well. So the formula, the general form, HNX. X is an anion. X is an anion, and very often it is a halogen, in group 17. But a lot of times it's some of the other nonmetals. Very, very often it is polyatomic, and all those polyatomic ions come in to help us with the acids here. All right, so if I have a monatomic anion like chloride, it has a charge of -1, and I would need 1 hydrogen plus, and I would have H plus and Cl minus, and that makes HCl, hydrochloric acid. That's the stomach acid that's in your body right now. Helps you break up proteins into their amino acids, and then it leaves your stomach and goes to the rest of your body, and allows you to live. It's a good thing. So there are 3 rules to help you name an acid. If it's got the general formula HNX, again, N is another variable. H is not a variable, it's literally H, it's hydrogen. N is just a number, and then X is the whatever else that is left behind when the H goes somewhere else. So you need to have the name of the anion, and you're going to know whether it's ide, ite, or ate, what kind of suffix there will be when you name the acid. So ide is going to be your first one. Remember, ide goes with the monatomic anions, so the 1 atom, so chloride, oxide, nitride, all of those. Ite and ate are going to be those anions that, I'll add this to the dictionary, are are going to be those that have oxygen, but 8 has one more than ite does. 8 has one more oxygen than ite has. So if it ends in ide, that should be all together. That's unfortunate. There we go. Then we start with hydro. Okay, hydro. Hydroide. If it has an ide, so chloride, we start with hydro. And then we have ic at the end. That's our new suffix. Our new suffix. So HCl, hydrochloric acid. So again, like that. Good old Georgia, HCl. So you know it's not HCI. And there, in that case, the Cl is X, right? That's the anion, and it's chloride. And it's hydrochloric acid, right? So you always, if it's an acid, you say acid. If it has just a monatomic anion, they will have an ide, and you take away ide and add ic and hydro. So hydrobromic acid for bromine, right down the list, hydroiodic acid, hydrofluoric acid, and so on and so forth. And let's see here. There's hydrosulfuric acid, H2S. Oddly enough, we don't say hydroxyic acid, but that would be another way of saying water, hydroxyic acid, or hydroxic acid. But we don't actually ever say that. So again, that's if the anion is ide. So first of all, we look at the formula, we say, aha, the X here is chloride, so I add the hydro and the ic, okay? So I look at the formula, I know it's monatomic, it's ide, so I add hydro and ic. So this is very common. There aren't a whole lot of them though. The larger number will have polyatomic ions. So, oops. So if it's ite, then it ends with us, O-U-S. So, O-U-S, O-U-S. All right. So H2SO3, again there, this anion is sulfite, and so we say sulfurous acid. We don't say hydrosulfurous, we just say sulfurous acid. We don't have to add the hydro. Don't add hydro as the prefix. Okay, you only add the hydro when you have an ide, not an ite. So sulfurous acid. Sulfurous acid doesn't come up very much. It does, in fact, actually, some people wonder whether it actually exists. Kind of exists more in theory than in actual fact. You can't get a bottle of sulfurous acid, but it only certain reactions only happen if it exists. So anyway, then we have 8, and 8 is by far the most common thing. And so here we have HNO3. NO3 is nitrate, NO3 1 minus rather, and so it's nitric acid. So ic again, just like with the monatomic ions, we have ic. So anytime you see an acid, it will either be us acid or ic acid. And then if it is ic acid, then you need to know, is it going to be, is there a hydro in front or not? Then you know about it. So for instance, hydrochloric acid and chloric acid both have hydrogen. They both have chlorine. But chloric acid, the anion is chlorate, which has 3 oxygens, and you'll learn that later. So once again, to review, you have your hydrochloric acid, your sulfurous acid, and your nitric acid. That's where we're going to stop for today. I do hope that you have a good Easter weekend. And, yes, you are dismissed. Bye-bye.
Have a good weekend.
You too. Keep getting things in that are due. Any of you who are still here have any questions I can help answer? Garrison, Alyssa, Taj, anything I can help with? Okay, then I'm going to go ahead and let you go.